with large-scale flooding with biblical connections. But some geologists towards the end of the 19th century thought somewhat different. And one man in particular, J. Harlan Brett, pioneered the concept that the strange, apparently erosional network of channels you can see bottom right here in the northwest of the USA had been caused by catastrophic flows of water. And you can see one of his sketches, top left there, that he produced from detailed field work, driving around and riding on horses. You know, he had no aerial photographs, he had no satellite images. And we have a lot of evidence in Missoula, such as very large boulders, so big, you know, could they have been moved by water? We have eroded channels with gigantic bars along the margins. We have dry waterfalls. We have gigantic gravel dunes. Now, you know, is this unique? And for a long time, Missoula was seen as a bit of a quirky, sort of exciting and interesting, but what's it to do with processing the rest of the world? Until, I think, only 20 years ago or so. But in fact, catastrophic deposits from terrestrial water floods are turning out to be really quite common. This is a compilation put together by Victor Baker across the different hemispheres. A lot of evidence in the northern hemisphere because of glaciation, but there's probably more to be found in South America if they just haven't been written up yet. And I'll be talking a little bit about the Altai, which is one of the symbols here, which you probably can't pick out in detail. So, one thing that struck me quite early on was, I have an interest in sort of hard rock geology as well, was I couldn't really find many references that identified catastrophic flood deposits in what we might loosely call the hard rock record, in other words, pre-Quaternary. And I sort of dug out 3 there, and there's a couple of question marks. I'm sure people will say, yeah, I got another one. But there's only a handful. And Emiliano Muti pointed out that the lack of recognition probably reflected the lack of models allowing people to identify catastrophic fluvial deposits in the hard rock record, rather than the fact that they didn't exist. So, if you don't know where the Altai is, I thought I ought to give you a quick lesson in geography. If you go down through Siberia, there's one place where the Siberian border is the same as the Chinese border at that pinch point there. And we're in the headwaters of the Ob River, draining north into the Siberian plains. And there's 2 main tributaries right near the border there, the Chua River and the Katun River. There's 2 basins, the Kure Basin and the Chua Basin. And those basins contained a very large ice dam lake in the Quaternary, which failed on occasion. So on the left here, we have the Chua and the Katun basins. You can see them. They're conjoined by a narrow valley. There was an ice dam. I don't have time to go into detail. And then to the right, we have a very steep river channel, the Chua River, which flows down and joins a lower gradient river, the Katun River, which is flowing from right to center and then down to the bottom of the slide. And that's a low gradient system. And on the right here, we have another basin. So the Katun is coming down here, the Chua is coming down here. And from our work, we know that we had an ice dam in here about 600 meters high. And this is a big ice dam in South America, just to get your eye in, so you can imagine the kind of environment I'm talking about. So the motivation for this is that the Altai is probably now at least as well studied as Missoula. And there's been phenomenal progress both in North American studies of catastrophic flooding, but also in the Altai, in developing models of the flood flow. Now, if we pull the plug out of the lake, the water's going to run out, and we know from other work there were probably 3 floods, and the various models all tend to tell us the flood was around about a peak of 10 million cubic meters per second. So we very rapidly moved from simple 1D models using HEC-RAS. Vic Baker did some work, very limited spatial extent. Jürgen Herget extended this to a much longer reach. I, with colleagues, compared 1D and 2D models, and we coupled it to an ice failure mechanism. Zhijing Chao has looked at bed scour and sediment transport. Huang has looked at the bifurcation where the Chua joins the Katun River, where we get some reversing flow as the flood drops. We've got more work being done on sediment transport within 2D models. And in one particular paper, Bohoquez tried to justify the location of stranded fossil gravel dunes from a hydrodynamic model. Could we explain why these dunes occur where they do using a hydrodynamic model? So we're now moving to couple hydrodynamic models with the bed forms we find in the landscape. So we're now moving on, trying to work on what we call whole system modeling, where we drain the lake through a failing ice dam and then route the flow down the valley rather than just route the flow down the valley. And future work, we want to be able to predict where, for example, gigantic gravel bars might be located down a floodway, or indeed use the presence of the giant bars to feed back in and inform our hydrodynamic modeling. So if we got a giant bar in a certain location, then our hydrodynamic and sediment transport model should take account of that. And in the long term, something I would like to see done is that could we actually generate synthetic sedimentary sequences which mimic what we observe in stratigraphic sections. So in order to do that, we have to know what is the typical signature of the stratigraphic succession within, say, a lateral giant bar or within a large gravel dune. And today I'm talking about the lateral large gravel bars. So we can either use our model to try to say, yes, this flood was catastrophic, or it wasn't catastrophic, however we might define that. Maybe catastrophic floods do have a characteristic signature. But more interestingly, can we use these sedimentary sequences and the change in the way the sediment is moving during a flood to inform our flood modeling? Now, we've not done this yet, but it's a very interesting idea, in my view, that might be possible. This is a section in a giant bar. The giant bar is about 300 meters high, so you've got to get your head around the scale of these things when you're in the field. So linking to the point I've just made about relating the sedimentary sequences to the progress of a floodway, various people, including Andy Russell, have argued that we get characteristically different shapes of hydrographs, depending, for example, if it's a dam break, very rapid rise, very rapid fall, but not as fast as the rise. Yoko Labs, he says, rise more slowly, but still rise precipitously, and then fall catastrophically. So these are simplistic ideas, but you get the idea that the hydrographs can be different for different environments. And of course, we're going to get perturbations on those hydrographs, particularly with an ice dam break. If it's through a tunnel, the ice tunnel might close and then open, or you might get huge amounts of ice getting jammed in the floodway, and that's going to cause fluctuations in the discharge. So in reality, we're going to have some kind of complicated pulsing flow down through the system. The hydraulics, well, we're talking about very high velocities. 40 meters a second is not unusual in many, many models. And you can test this for uncertainty. Depths in some occasions were up to 300 meters. And of course, extremely unsteady, but massively powerful. And I'll come on to the question of power in just a minute. They clearly can carry a very high sediment load, and did. There's a lot of floating ice, which can complicate our interpretation of the hydraulics and our interpretation of the sediment. But generally, these are linear events. They have a distinctive source, they have a flood tract, and then they have a depositional zone. And this can help us in some respects. So I made this little cartoon here. It's a bit small. We've got a lake, which is the source. We have a dam, which breaches. The breach area can also supply sediment from the ice mass. We have a transfer zone, which can be confined, for example, a mountain valley, and then there'll be a distal zone where sediment can spread out and be deposited, and it might actually make it into a lake or an ocean. So the stuff I'm talking about today is in zone 3, and though it's confined, all mountain valleys have tributary valleys coming into them, and they have alcoves in the side walls. They could be, say, small corries or just small gullies coming in. And these areas are potential repositories for sediment as it comes down through the flood. So a steep mountain valley is not just a conveyance zone moving sediment from the dam breach area to the distal zone. And there are a number of typical types of bars you can form. If you have an expansion, of course, sediment will drop out, so-called expansion bars. They tend to be very, very coarse. I'm not talking about those today. They can form on the inside of the bend, exactly analogous to a point bar, but the scale is very large. And they can form downstream of obstacles such as isolated hills in the middle of the floodway. And in particular, on the margins, they can backflood into tributary valleys. So in the shear zone, we often find extremely coarse material, which then finds back into the tributary. And importantly, I'll come on to this later, as that fills, there's often a slope going back into the tributary, a depositional slope. The tributaries don't get fully formed. And when you go into the field, you can walk up the outside of these bars and then walk down into the tributary valley. Usually, of course, the tributary later has breached these deposits, and you can often have very nice sequences. And we need to remember this environment to understand some of the concepts I'm coming on to. So some pictures to get your head around. This is the Chua River flowing right to left. This is a Holocene terrace with the village houses on it. And in the background, there's a giant bar here. This is the top of a giant bar. And it's breached these days. You can see there's a low area here. It's breached by a tributary river which is coming out through this giant bar. And if you walked up over top of this, you can then walk down the back of this bar into the tributary valley. I've got a better picture later to show that. Huge sections in the main valley. You can see rhythmicity in the sediments here. These are fine gravels. And here's some other interesting features. Very thin bars along the margins. These are not terraces. And if you do a hydraulic model, you can match the water surface slopes as the flood falls to these smears of sediment dumped out along the margins of the valleys. Now, this is looking downriver. The Khatun River is coming along here. I'm on top of the giant bar taking this photograph. The river comes around here and disappears down here. There's a tributary valley coming in from the left here. And here's our giant bar, which has been dumped out in the mouth of the tributary. And you can see the slope going back into the tributary. And you can walk down that slope back into the tributary. Now it's been breached by the tributary flow at later times coming through here. And if you walk up into these, I'll call them corries, they're not necessarily glaciated, they're all smeared with small fluvial pebbles. Because of unsteady flow, sloshing up into the margins of the channel as you go down to the system. All the sediments up in here, they're not scree, it's water deposited material which is sloshed up into these side valleys. What I found, you can't see this, you don't need to, is that you get repetitive sequences that, if you look at the big picture, are repetitive. We seem to have one flood pulse, a second flood pulse, a third flood pulse, a fourth flood pulse, and these sequences should tell us something about flood behavior. Now, when we look at river sediments, what do we usually look for? Traction is always gravel. Yeah, if we see gravel, we expect it to move in traction. Sand and silt, we think, yeah, it can move in traction, but it's probably going to go into suspension, and we might expect to see turbidity currents. Sorry, we might expect to see debris flows. But we don't really expect to see anything that looks like a turbidity current deposit, because we're dealing with the fluid end here, and we've got the debris flow end up here, and in the intermediate areas, we've got high concentration flows which have some kind of possible non-Newtonian behavior. And this point came up on Monday when we were talking about some of the flows of bedload in the Swiss Alps. Does the rheology change when we have extremely high transport rates? So we're not usually used to looking at this stuff here. Now, in the turbidity current literature, there's a classic model called the Baumer model of deposition from a turbidity current, from the waxing flow and the waning flow, and it produces a systematic series of units as the flow waxes and as the flow wanes. And what I noticed with the megaflood deposits was that you had series of stacked units which were very similar to the Baumer model. And when I talked to other geologists, they said you can't possibly invoke the Baumer model because it applies to turbidity currents in the marine environment and it only applies to sand. And I thought, well, if you have enough energy and you can move gravel, I don't see why, if you alter the rheology, you couldn't generate a similar sequence. So I'm not saying we necessarily have turbidity currents, but we certainly have high turbidity currents if we don't actually have technically turbidity currents as the marine biologists would like to define them. So when we look at these deposits in the field, we not only have to suspend our gravel, we have to suspend our disbelief that gravel can be suspended. And we know from limited measurements on yokolauts that the powers are high enough to move 20 centimeter diameter class in suspension, and some of the short peak yokolauts can suspend 2-meter boulders. It's been observed. And the largest quaternary floods had powers 1 or 2 orders of magnitude at least larger. So these were sustained over many days, over great distances, and they didn't only pick up blocks, but they can comminate material. They can break it down. So often the sequences we see aren't formed of sand, they're not formed of pebbles, but they're formed of smashed up native bedrock that was probably pebbles and cobbles originally, or it was ripped off the valley walls. And you find lots and lots of angular gravel to find pebble-sized material. So we cannot preclude the possibility of deposition of gravel from high concentration suspension. So linking to this idea that the Baumer sequence seems to have analogues within our gravel sequences, the issue was, can we pull any generic signatures out of our sequences? And here is one rhythm in the Altai, and if you go up through the sequence, basically the same rhythm is repeated in some places 6 to 11 times. There's some variability, of course, but you start at the bottom with a basal sequence of sub-parallel, sub-horizontal beds of cobbles, and very poorly sorted. And this is typically deposited at the entrance to one of these re-entrants on the beginning of the flood, when you get powerful surging into the entrance of the tributary. And as the flood thickens and begins to prograde into these tributaries, you get various clinoforms on top of those coarse gravels. As the flood continues to deepen, you tend to get lots of laminated fine gravels, subparallel, sub-horizontal wavy beds. I can show this later. A little bit of debris flow material, probably sloughing off the valley walls as the flood destabilizes the flanks of the valleys. And then, as the flood begins to lose power, you get small bed forms. They're never large because you're in quite coarse material, but you get things which are trying to develop it as ripples or small dunes, cut and fill, and then as the flood finally subsides, you get silt dumped out on top, which is the end of the sequence of the Bauer sequence. And sometimes you get debris flow spreading over the top of the unit at the end of the event. So that's a very, very typical sequence in the Altai. Now, going through the literature, I begin to realize that many other catastrophic flood deposits around the world have similar motifs with variability. Sometimes one sequence of the Baumer model is missing, sometimes the sequence is thicker than you'd expect, but the basic sequence remains the same. So this is an example from one of Judith Basil's papers from Iceland. I'm not going to go through the detail here, but at the bottom we've got sequence 1, then we've got sequence 102, sequence 3. This is the waxing phase of the flood, and then we have sequence 4 and sequence 5 during the waning stage. Now, it's not unreasonable as the flood strengthens and weakens that we should see repetitive behavior. The physics is the same all the way around the world, so all big floods should be laying down pretty much similar sequences as long as the material is available for transport. So, examples of these basal sequences. This is an example from the Pleistocene in the southern Apennines. There's massively thick, unstructured beds here of cobbles, repetitive sequences of cobbles. The very big section, there's actually somebody stood down here. You won't be able to pick that out. But you've got about 50 meters of cobble beds there at the base of the sequence. This is the base of the sequence going into a tributary in the Altai. Huge clinoforms, big clinoforms here again. And here you can see right at the base, very thick beds of cobbles. So this is a typical sequence: cobbles, then some clinoforms, massive, often very angular, from the first influx of coarse sediment. So here's just to remind you, when the flood first arrives, it dumps out a lot of coarse material in the reentrant, and then sediment begins to grade over the back of that coarse sediment as the flood deepens. And I mentioned the clinoforms. What is incredibly distinctive is that these clinoforms are migrating into the tributary, which is just a back-flooded embayment. And here we have some examples. This stream here is running from bottom left to top. The main river where the flood came down is running right to left in the background. And you can see the forceps, these clinoforms, dipping up valley into the tributary. And here, one of my Russian colleagues has stood in the water, so you can actually see that the tributary is flowing right to left and the clinoforms are going back up into the tributary. This absolutely amazed us when we first saw it.
5 minutes.
5 minutes? Is all I've got left? Good God. Well, I didn't realize it was taking so long. All right, I'll go quickly. As we move up into sequence 3, we get these finer gravels dumped out from high concentrations onto weakly mobile beds, and they're incredibly distinctively laminated. This is a really clear indication of catastrophic flood deposits, the rhythmicity. And as we come to the end of the main flood pulse, we begin to get rippling. This is all in fine granules, trying to form some bed forms as the velocity drops. And you get beautiful rhythmic sequences. This is from Iceland, much smaller scale, only a couple of meters. But silt layers dumped out after the end of every pulse or every flowing vent. This is an example from Chile, where a lahar that's actually diluted by water flow is dumped out of sequence, is capped off by silt, then it repeats again. And finally, they're often capped by thin debris flows. Here we have our laminated gravels, then we have these debris flow units on top. During the main flood, there are debris flows because the floods are destabilizing screes and other material on the flanks of the valleys. And those slough off into the flood. But they get consumed and amalgamated and lost. But as the flood drops, that stuff is still sloughing off the sidewalls, and in the quiescent conditions at the end of the flood, you get some thin debris flows just coming out on the top of your catastrophic flood deposits, giving these capping units, marking the end of a flood sequence. They're very rhythmic. Sometimes you can't see trends in grain size until you sample them. You see here, it's coarsening upwards, but you wouldn't see that in the field. And I can move to my collusions pretty much on time now. With this kind of approach, we can make a comparison with the behavior of the Bowman sequence for turbidity flow, or turbidity currents, with the kind of sequences we see for megaflow. Here's our 5 units again. This is written up in part in this conference volume. There's a much fuller exposition in Earth Science Reviews in 2013. And we've been able to develop conceptual cartoons of how sediment builds up in a tributary. Here's a tributary coming in here from right to left. The main flood is coming out of the screen towards us. And sediment is introduced into these embayments, building up from coarse in the area which is proximal to the main flood. It finds distally into the tributary. And with flood pulsing, or series of floods, you get these repetitive sequences. So we now have a nice, if you like, standard model for catastrophic flood deposition that we can use to interpret other sequences. Now, somebody might already have a sequence of catastrophic flood deposits and note that it doesn't actually match what Carling is describing. Well, I really like this idea of Roger Walker's. You take a number of examples from nature. I've put a number of locations here. Icelandic Jökulárlón, Missoula, Altai, Himalayan floods, turbidity currents in the marine or from the laboratory. What's the other one? Bonneville, Lake Bonneville outbreak. You distill that information and you come up with a model. You can either use that as a direct predictor, or you can go back and make comparisons and use it as a norm. And then a model becomes very powerful because you can identify where there are differences from the norm, and that can be important. And it provides a framework for future observations. It helps you decide what you need to be investigating to better understand your sequence compared with, if you like, the standard model. And it provides an initial basis for interpretation. So if your sequence differs from what I've described, it's actually a useful observation rather than a reason to reject a standard model. So don't worry too much. You know, I met this guy in the Altai. He didn't seem very worried. So take the model, apply it if you can, and if it doesn't work, well, just reflect on why it's not working. Thank you very much.
Thanks a lot. Well, So now let's open the floor for questions. Oh yeah, sorry. Sorry. I was too excited to make a question myself. So now, yeah, we welcome Mikael Attal. He is from Scotland, from the Department of Geoscience, School of Geosciences, University of Edinburgh. And he will tell us on how sediment supply can quite affect the sediment transport. Thanks.
Thank you, Francesco. It's already starting. Good morning, everyone. Konnichiwa. It's a great pleasure to be here today, and I'm going to talk about the linkage between sediment transport, which happens in the river and that most of you are very interested in, but I'm going to see how that sediment transport links with what happens, the sediment supply essentially coming from the heat slopes in mountain rivers. So this will apply to mountain rivers. And this is what I'm going to talk about for the next half an hour. I'm going to briefly introduce what I mean about mountain rivers. Then I will talk about how sediment availability in a river varies in space and time, and how that links with sediment supply. Then I will talk about how sediment export from a given reach is going to be the result of the interplay between the flood magnitude but also sediment availability. And then, because this session is about extremes, I'm going to talk about extreme grains and extreme floods. So we're going to start with an introduction to mountain rivers. Most rivers tend to start in the mountains, where they tend to develop a sort of mixed bedrock alluvial morphology. There's going to be bedrock exposed, the river will be eroding. And most rivers are going to flow into a lake or into the sea. And as they approach the lake or the sea, they're going to develop a sort of alluvial depositional behavior. And that transition can be abrupt if you are in a tectonically active area. It can be more gradual if it's not tectonically active, like here in Scotland. When you are in the alluvial reach, the river can be considered transport limited in the sense that there's a lot of sediment available, and the amount of sediment that will be transported out of a reach is going to depend essentially on the transport capacity. Sediment is plentiful, and as long as the river exceeds the flow competence, the flow competence allows sediment transport, then you're going to entrain sediment. When you are in the mountain reach, there's going to be a problem of sediment availability in the sense that there's not always a lot of sediment available for transport in the mountain reach. And that's the point that I've tried to illustrate with that very simplistic diagram. So here, what I'm trying to represent here, this is a river reach. I'm considering that reach. And that's the sediment available within the reach per unit time. And here, that little square represents the transport capacity of the river. That's how much the river can entrain per unit time. And here we've got a grain size issue as well. This is the maximum grain size that the river can entrain at that time. So let's focus on the left-hand side first. You can see that all the sediment grains are smaller than what the river can entrain. So you're going to have probably full mobility. The river will be able to entrain everything. And in the first case, you can see that there's more sediment than the river can transport. So the amount of sediment that is going to come out of that reach is going to be limited by the capacity, transport capacity of the river. Because we're in a bedrock river, in a mountain river, you can also have that situation where actually the river can transport a lot of sediment, but there's not much available. So the river will be under capacity, and the amount of sediment that is going to come out of that reach is going to be limited by how much sediment is there. So here we've got full mobility, these two scenarios. I try to illustrate here also the fact that there's a grain size effect as well. Depending if you've got grains that are much larger than what the river can entrain, you will have partial transport. And again, in this case, you can have a situation where you are at capacity or under capacity. This is a very simplistic diagram. It doesn't take into account armoring effect, hiding effect, jamming of clast and so on, but it's just to illustrate the point that the grain size and the amount of sediment that is going to be transported out of a reach during an event is going to be a function of the flow competence, the transport capacity, but also the characteristics of the sediment available in that reach, and that's the amount of sediment and the grain size distribution. Right, so this sediment availability is going to change in space and time, and that links with the sediment supply. There's been a few studies that illustrated that point, and I'm going to talk about that. One of the main reasons why you've got this variation is that sediment supply is episodic, tends to be an episodic process, and it tends to be spatially variable. So what I'm going to talk about in that section is, firstly, I'm going to talk about spatial variation, so there will be this little logo here appearing here, and then I'm going to talk about temporal variation. So let's start with spatial variation along the river. And some work that I did with colleagues over the last 10 years show that you can have spatial variation in the grain size of the sediment, for example, that are linked to changes in source of sediment. So I've got 3 examples here of types of source. Rivers can tap into glacial sediment, like here in the top of the Marsandi River in the Himalayas, and that's going to have a given grain size. Rivers can flow on low relief landscape, soil mantle, and that's going to, the soil are going to supply another type of sediment. And river can flow, can incise rapidly into a steep landscape, and in that case, again, you're going to have another signature. You're going to have scree, you're going to have landslide, and that's going to have another signature. And in this example, for example, along the Marsandi River, here we are going downstream the river. This is the distance in kilometers. And this is the grain size of the sediment in the river. So we've got here the median grain size of the subsurface and the median grain size of the surface in blue and red, respectively. And what we saw is that the grain size is relatively stable, and then you reach a point here where the grain size of the sediment on the gravel bar increase abruptly. And this point coincides with the transition from the place where the river is tapping into this glacial till to the place where the landscape suddenly steepens and you've got a lot of landslides bringing additional coarse sediment into the river. So we measure the grain size of the sediment in the till and in the landslides, and even if in the till you've got very large blocks, you still end up with sediment which is globally, generally finer than the sediment provided by the landslide. Similar observation in Italy. Here we are in a situation where we've got a river flowing across the fault, so we're going downstream here. We've got a fault, and the fault accelerated around 1 million years ago. And as a result of that, you have a landscape where you're basically, the river flows in a low relief soil mantle landscape that looks like that. And then suddenly there's a nick point along the river steepens suddenly, and you end up in a gorge, in a steep landscape with a lot of landslides bringing coarse sediment. And again, we see that same signature. In that case, this is subsurface sediment, D50, and the median grain size and the D84 here. And again, we've got a very fine grain sediment. And then the moment you reach that nick point, suddenly you go from the plateau to the steep landscape, and the grain size of the fluvial sediment increases rapidly. We've made similar observation in the Feather River in California here. So sediment supply is going to be spatially variable, and that's going to influence the availability of the sediment in the river, the availability of coarse sediment in that case. Now we're going to talk about temporal variation, and that's essentially due to the episodic nature of sediment supply. So we've got point sources, for example. Let's talk about point sources first. And this is a model by Banda and Dunn, where they showed, depending on where you are in a river network, in a river basin, this represents the sediment depth in the channel as a function of time. This is the time in years. And you can see that here, if you are in a small catchment, you've got no sediment, and then you've got these pulses of sediment that are the result of episodic sediment supply into the channel. That can be landslide, that can be dry gravel following fires, for example. And you can see that you end up with no sediment, a meter of sediment, no sediment, a couple of meters of sediment. So you've got this variation. You go from no sediment to a lot of sediment in the channel. And a place where there's a nice illustration of that is a Mosaic Canyon in Death Valley here. We've got a catchment which is around 10 square kilometers here. It drains, you've got marble and schist, quite contrasted lithology. And the river developed this very nice fan here, and at the apex of the fan, it's incising into the fan. And that's what the deposit looked like. And so you've got beautiful landforms here, beautiful features formed by abrasion. But what is interesting is to look at the difference in the grain size and the nature of the sediment that is coming out of this catchment. In some cases, it's 95% small, rounded schist clast in black here. And in some cases, it's 95% coarse, angular, marble clast that come out. So this is the same river exporting that sediment, but sometimes it's just almost entirely schist, and sometimes it's entirely limestone. So the best way of explaining that, of interpreting that, is in terms of availability. Sometimes there's a lot of schist present in the channel ready to be entrained, and sometimes there is a lot of limestone. That can be due to debris flow processes as well. You can have that illustrate the point source in the sense that the sediment may come from different parts of the catchment, and as a result of that, the sediment being exported by the river can have very different characteristics depending on where it comes from. So this is for point source, but you can have also some basin-wide sediment supply into the channel. So in that case, people have identified that you can have external drivers of sediment supply. That could be storms, that could be typhoons, that could be earthquakes, and then one happens after the other. It can be pretty dramatic. And here we've got a valley here with an approximate scale, and I'm showing here a few examples. Lane et al. In the Yorkshire Dales in the UK showed that, for example, following powerful storms in summer, you tend to generate a lot of shallow landsliding, and that generates a couple of meters of aggradation into the tributaries of the main river in the area. So here, there's no sediment, and then you've got these storms coming, and suddenly you've got a lot of sediment coming into the tributaries, and you can have up to a couple of meters of sediment in the channel. In Taiwan, following the Chichi earthquake and the typhoon Toraji, Datsun et al. And Yanitas et al. Showed that there was widespread landsliding, again, a lot of sediment coming into the channel all over the affected area, and that led to up to 18 meters of aggradation into the channel. So a lot of sediment, again, there's no sediment, and then suddenly a lot of sediment comes into the channel. And the most extreme case I've seen is by Pratsi Thorai along the Marsandira Valley, where they showed that between 50 and 35,000 years ago and 8,000 years ago, the river aggraded around 100 meters. So they interpret that as a result of monsoon intensification. The hill slopes destabilized on a quite grand scale, and that led to the river not being able to deal with all that sediment, and a lot of sediment being deposited here in this valley. So here again, sediment supply is temporarily variable. You go from no sediment to quite a lot of sediment, and that's going to influence how much sediment is going to be exported by the river by the subsequent floods. So here, let's talk now about the sediment that gets exported. And because there's that issue of sediment availability, that means that the largest flood will not necessarily export the largest amount of sediment. Again, very simply explained here, we've got two scenarios with a river under capacity. So the river, in both cases, is able to transport all the sediment that is there. And in that case, we've got a small flow with a lot of sediment. So all that is going to be exported. And in that case, we've got a large flood, but there's not much sediment available. So again, you're not going to transport much sediment out. And I'm going to talk now about the trade-off between the amount of sediment available and the transport capacity. And then I will talk about the grain size and flow competence with a few examples here. In terms of amount of sediment, Jens Turoski here came up with a nice conceptual model to illustrate behaviors that they've identified in a series of rivers. And here in that case, QS, the sediment supply to a given reach, is a power function of the discharge with an exponent lambda. What we have here is the discharge of the river, so the discharge increased towards the right. And in the top diagram here, we've got lambda is greater than 1, and this is what they describe as a flood depositing behavior. In that case, you can see that the line, the dashed line, is the sediment transport capacity. It increases linearly with the discharge. And here, because lambda is greater than 1, the sediment supply increases faster than the transport capacity. So at high discharge, you end up with more sediments being supplied to the river than the river can actually transport. So the result of high intensity flood is going to be net aggradation in the channel. There's just a lot of sediment that gets supplied, more than the river can deal with. And at the end of a big flood, you're going to end up with a situation like that. And then you can see that for small floods, the transport capacity is greater than the sediment supply. So the small floods are going to progressively evacuate the sediment that has been accumulated following the large flood. In the other scenario, if lambda is smaller than 1, this is a flood cleaning behavior in the sense that big floods are going to really clean the river reach and create a lot of erosion. So this is an example from Eastern Australia, Paradise Creek, looking paradisiac, and then not very much anymore. And you can see that here, at high discharge, the sediment supply increases more slowly than the transport capacity. So at high discharge, there's less sediment being supplied than the river can transport, so you score. And at low discharge, then in that case, small floods are going to provide sediment into the channel. You're going to have aggradation, and big floods are going to flush that out of the reach. The only problem is that what Jens and colleagues have shown is that this behavior is alternating in space and time. So along a river, you can have some flood depositing reaches and flood cleaning and flood depositing. And in time, that changes as well. So a flood cleaning reach can become depositing a bit later. So, and that seems to be really due to the link with sediment supply, essentially from the heave slope. And it's inferred that the aggrading phase, so during the large flood for flood depositing or during the small flood for flood cleaning system, are probably synchronous. The sediment supply is synchronous with the aggrading phases in this case. And what is interesting to note as well is that despite being in the mountain realm, extreme aggradation, like the one I showed in Taiwan or in the Marsandi River in the Himalaya, can make the river transport limited for centuries to millennia. When you've got 10, 100 meters of sediment, it's going to take that amount of time for the river to evacuate that sediment. So sediment availability is not going to become a problem. And in that case, the grain size is going to become the limiting factor for sediment transport and entrainment. So let's talk about the grain size of the sediment available. So as I showed earlier in the first part, there is a strong source control. And in some cases, the grain size of the sediment transported can be limited by the coarseness of sediment available. In soil mantle landscape, and we saw that in the Feather River in California as well, if you've got low relief soil mantle landscape, we found that there's no coarse sediment. Like in that case, the largest class that we found in the soil or even in the river was that size. So even if a very large flood comes, it's not going to be able to entrain coarse class because they're just not there. There was another example that showed that by Matter and Hartley. Here we are in the Atacama Desert, and this is a fan. And we've got here a large class of volcanic rocks. So obviously the flow had the capacity to entrain class that size, but most of the sediment is very fine grained. And again, Paul showed some example of that as well. There's a lot of gravel that makes that sediment. And in that case, they interpret that also as a result of the fact that in the source area, the source rock is just a conglomerate made of gravel. So even if the river can transport very large blocks, the large blocks are just not there. So they're not going to be exported by the river. In other case, the grain size of the sediment is going to be the grain size of the sediment transported is going to be limited by flow competence. And that happens if you've got a steep landscape. Landslides, creeks, tributaries are going to bring quite a range of size, and the river is going to pick what it can based on its competence. And in that case, boulders can have a big impact on sediment exported by the river. That brings me to the fourth part of the talk. We're going to talk about large grains and large flood. I'm going to start first with the influence of boulders on sediment export during floods. And then I will talk about the influence of extreme flood events on sediment export by subsequent floods. Let's start with boulders. When boulders are present in rivers, they tend to lead to the development of a step-pool morphology. Hopefully I'm not teaching you anything here. And these morphologies tend to be stable for moderate, low to moderate flood. Only high magnitude events are going to be able to break the steps and free the sediment which is trapped within the steps and potentially expose bedrock for erosion. In some cases, when boulders are abundant, that can lead to, probably going to raise a few eyebrows, to what I call bedrock aggradation. In the sense that in some cases, there's so much large clast that the large blocks are going to behave like bedrock. Here we've got a percent for scale in the Feather River. You can see that these blocks are not going to be moved by even high intensity flood. And here this is an example from the Marsiandi River in the Himalayas as well. You can see that some of these boulders, this is seen from above. The river is flowing in that direction. And you can see flutes and potholes that probably developed over years, decades, maybe centuries. So these features are stable on the centennial to millennia scales. And they behave like bedrock. And only extreme events are going to be able to mobilize a significant fraction of the boulders. And the result of that is that that can lead to a long-term channel adjustment to these boulders. I've got a couple of examples here. The first one is in the French Alps by Broca and Van der Beek. And we've got a river profile here, the Mares River. And what they showed is that the gradient of the river is adjusted to the rock type eroded. So when the river flows on Mars, it's low gradient. When it flows on limestone, so we've got a limestone bar here, we've got nick points developing. But what they found is that between the two limestone bars here, the river flows on Mars, but it's still very steep. And what they found is that in the field, the river here was completely covered in boulders, limestone boulders coming from the hillside. So here they interpret that as the fact that the river is behaving as if the bedrock was limestone. The limestone boulders are behaving like, are making the river behave as if it were flowing on limestone. There's another example by Joel and colleagues here, Joel Johnson. Here we have rivers flowing, incising into sandstones. And what we have here is that some rivers don't have much sediment, like the tributary 43 here. And some rivers have a lot of diorite boulders, like Trail Canyon on that left-hand side. The rivers are incising into the same rock type, but you can see here this is a slope as a function of drainage area. The squares are the Trail Canyon data, and the circles, the solid circles, are the tributary 43 data. And you can see that for an equivalent drainage area, the Trail Canyon is steeper than the tributary 43. So the channels which have the boulders tend to be steeper than the channels without boulder. And that's interpreted as a long-term adjustment. What the boulders are doing, they're basically making the bedrock more resistant to erosion. So the rivers need to get steeper to adjust to this, to provide the extra power that is going to be needed to create some incision. Okay, let's talk about exceptional floods now. When I talk about exceptional floods, so it's essentially the availability as a function of transport capacity here. Grain size is not an issue because these floods are going to lead to full mobility. We're talking about floods with a recurrence interval of typically greater than a century. They're going to produce major landscape change that can be through sediment transport, deposition, bedrock erosion. And they can be caused by a variety of cause. That can be powerful storms or typhoons, that can be landslide dam break, and that's quite common in mountainous landscape. Glacial lake outburst, subglacial volcanic eruption. And in that case, as I said, you're going to have full mobility. These are the sort of clasts that are going to be transported. And in that case also, you're going to have a colossal amount of sediment that is going to be transported by the river. So you're going to have net sediment export from the mountain to the basin. That can be the ultimate sediment basin, or it can be local basins like the Altai basin, for example. And despite that, as Jens' work showed, the flood can have a flood cleaning effect, so you can remove a lot of sediment. But because a lot of sediment can be supplied to the channels at the same time, they can also have a flood depositing effect. The result of that is that extreme floods can have both effects. They can inhibit subsequent sediment export through that cleaning effect. So we've got an example here from Iceland. This is the Yokulsa Fjordlung flowing north. The Dettifoss waterfall, most powerful waterfall in Europe, is here. And there's a history of extreme floods, of large floods coming down that channel during the Holocene. And this is the path that the floods have followed. What we see here is that if you take a picture from here, you can see that these mounds are made of glacial till. There is a lot of glacial till available with very fine-grained sediment, a lot of plast here. So all that is glacial till. You've got an island here in the middle. But then when you look at what's in the channel, it's just bedrock. The bedrock has been completely cleaned of the till. So you could imagine that in that case, if another big flood came down the same way, the first one had a lot of sediment to transport. The next one will not have much, and it's going to have to essentially deal with bedrock. And that's what I try to exemplify with this very schematic diagram. Here we have the amount of sediment exported from, consider a river reach. This is the amount of sediment exported as a function of time, and this is one big flood. So you can see in that case, in gray, the flood exported a lot of sediment. And in white, that's the bedrock contribution. I'm considering that in that case, the sediment got flushed out and the river entrained a bit of the bedrock. And then here I've got what I've called time for sediment replenishment, which is to bring as much sediment as was before the big flood. So if another flood of a similar magnitude happens after that time, again, you're going to probably export the same amount of sediment and the same amount of bedrock. But if you have another big flood happening shortly after the previous one, you can see that the amount of sediment that is going to be exported is going to be very different. First thing, there's not going to be any sediment transported, so all the sediment is going to come from bedrock erosion. And here I put three scenarios. The first one here is in the case where bedrock is easily entrained, easily broken. And in that case, the bedrock erosion is limited by transport capacity. So in that case, you may entrain, you may export the same amount of sediment than in the first case, except that it's all going to come from bedrock. So in terms of the characteristics of the sediment, it's going to be very different. You're going to have probably much less fines. It's probably going to be much more angular. And the source is going to be more local as well. If the bedrock erosion is limited by weathering, so fracturing, for example, you may end up with exporting the same amount of bedrock than in the previous case. And if bedrock erosion is really controlled by tools for erosion, the sediment particles impacting the bedrock, then in that case, the fact that there's no sediment may inhibit bedrock erosion. And in that case, you may have even less sediment, even less bedrock erosion, just due to the limits, the low amount of tools available. So here this time, sorry, 5 minutes, thank you. So here this time for sediment replenishment is a general concept. If you are in Taiwan, where you've got a channel incising, coupled hill slopes, this time for sediment replenishment may be a few years, a few decades. When you are in a place like Iceland like that, you may have to wait for the next glacial period to have more sediment deposited in this place. So that's for the amount of sediment. The extreme floods are going to inhibit subsequent sediment export also through the formation of stable boulder bars, for example. So in that case, I mean, this has been shown in many places. Big floods are going to transport sediment, and at the end of the flood, you can end up with quite a lot of large boulder bars. And moderate floods are going to struggle to deal with that. So you may have to wait until the next large flood to mobilize that sediment. However, there's been a few examples that show that extreme floods can enhance subsequent sediment export. And that's through a couple of processes. There's been some examples in the Alps, some examples in Taiwan. And the first one is hill slope undercutting. This is an example by Morche and Schmidt here. There's been a glacier, it's not a glacier, a lake dam break here. So this is before, this is after. And as a result of that, they found that when the flood came down, it undercut the hill slope. And the result of that is that it reactivates by undercutting the toes of the hill slope. You reactivate the hill slope, and you're going to generate, you've got a feedback process where you're going to increase the sediment supply into the channel. There was Archer et al. In Taiwan also shown a similar example where they showed that the biggest flood that happened into their channel widened the channel rather than caused great incision. So big floods can widen channel and reconnect and destabilize hill slopes. So you're going to have a lot of sediment coming in. And then the second effect is the destruction of resistant landform. If you've got a big flood, it's going to break the sort of step and pool morphology that you can see here. There's no more steps, no more pools here. The boulders are still there. But what these people have shown, and others in the Alps, is that after this big flood, the sediment yield increased significantly for moderate floods, for example. Right, so time to conclude. So here we were talking about mountain rivers, and here are the few points that I wanted to make. So the amount and the grain size of the sediment exported during a flood is a function of flow competence, transport capacity, and the characteristics of the sediment available for transport. And that can be the amount of sediment and the grain size. And what I hope I showed is that these vary in space and time due to the episodic nature of sediment supply and the fact that different sources are going to supply different type of sediment. So whether you've got a glacial sediment, soil, or landslide. These things can change in time as well. If you've got glaciation, if you've got glaciers that become more extensive, less extensive, you change the distribution of the glacial source, for example. If you've got an increase in tectonic uplift, you have a low relief landscape, and suddenly the landscape gets steeper, you get coarser sediment being supplied from landslides, for example. And when it comes to extreme, boulders are common in mountain rivers, and they can inhibit sediment transport and bedrock erosion when they are abundant. Extreme floods are going to be crucial in mobilizing the whole grain population, including these boulders. And they can be flood cleaning or flood depositing, and that's a result of whether you supply a lot of sediment from the hillside at the same time that the flood happens. So the timing between the floods and the sediment supply event is going to be crucial here. And the big floods can also inhibit or enhance sediment export by subsequent flood. So I think the last point is that I think we should try to pay more attention to the sediment supply process when we try to understand and predict the development of stratigraphy and sediment dynamics in mountain rivers. I don't know yet how to do that. That's what I want to work on in the future. But I think we really need to pay more attention to what's coming from the hill slopes. So thank you very much for your attention.
Yeah, thanks a lot, Michael. So yeah, now it's time.
Personally, in fact, I would like that you elaborate a little bit, because I don't see I don't see a direct link between the sediment supply and the flow discharge, and also I don't see how, why. I mean, conceptually, this relation, there is no reason it is monotonic or even continuous. So if you could a little bit elaborate on this.
Okay. No, I agree. I mean, in the sense, it is a conceptual model in the sense that here we're talking about sediment supply from upstream and sediment supply from the hill slopes as well. So in that case, you could see that the relationship is not direct, but the discharge is going to be a function of the drainage area. So so if you've got sediment coming from a catchment, so the greater the catchment, the greater the discharge. So the greater potentially the sediment that gets to that point. And the second point also, I agree that it doesn't have to be monotonic because there's the link with the hill slopes as well. So if you've got the discharge is going to increase as a result of rainfall, and I think that's one of the key points here is that if you think that as you increase your rainfall, you're going to increase the sediment supply in the river just by having more sediment entrained from the hill slopes, for example. So that's probably the most direct link is the link between rainfall and sediment supply from the hill slope. But I agree that it doesn't have to be monotonic, it can be stepped, and this is just, we don't know much about this,
okay,
process. So.
Yeah, in that case you're saying that rainfall is the link, the flow discharge depends also on the rainfall. But maybe there is also a correlation with the temperature, because you know, in some area there is a frost-defrost sequence, yes, especially in areas, for example, in southern French Alps, it's very typical, where it's below zero, above zero, and so in fact there is a strong seasonality due to frost-defrost sequence, which may be another. Okay, but it's very complex anyway. Thanks very much anyway for the nice talks.
Yeah, those Michael.
No, I'm here.
All right, now I understood the technique. So thank you both for excellent talks. So my question is more for Michael. So you're showing a really, really important piece of information that we're maybe overlooking, and maybe slightly more extreme environments you've gone to slightly more extreme environments to make the point, but it seems very relevant for just basic transport predictions and paleo reconstructions and your everyday gravel bed rivers. So how can we start to include this in modeling? Because it's making the point that antecedent conditions, which we see when we look at hydrograph and transport, it seems to be extremely important. So the same discharge isn't transporting the same amount of sediment, and the influence of tributaries and the nature of the sediment they're bringing. So how can we, I mean, it just seems to be making it seem kind of impossible. How can we start bringing this into?
I would say, I mean, not necessarily impossible. I mean, there are a lot of people working on that, I would say, but I mean, we need to understand the triggering mechanism for sediment supply, I think. And also, like, when you've got, I mean, there's different places in the landscape where you need to do that. So how do you supply sediment into a channel? From that point, how do you entrain it? You know, like when you've got a landslide deposit, it's not all suddenly available for the entrainment. Like there's going to be some of it is going to be partly on the hill slope, some of it will be in the channel. There's going to be different blocks of different size. So how do you entrain the sediment that has just been supplied? And then how does it get translated downstream? So there's been some work by Cui et al. Who try to model the behavior of, do you just translate the sediment pulse or do you progressively disperse it? So I think we need to do more work there. And there's the Potsdam group that is doing quite a lot in the Himalaya now. I think the Nepal earthquake, as tragic as it was, is probably a fantastic opportunity for trying to understand how, you know, a lot of landslide are providing a lot of sediments in the Himalayan rivers, and that's going to come down and that's going to hit the India very in the next years. And we don't know, is it going to be a massive burst? Is it going to cause a lot of increased flooding? So there are different places in the landscape where we need to focus, but I think modeling and having some examples where we can test the model is probably going to be, that's the approach I see for that.
Yeah. So. but maybe it's better to introduce. Yeah, please, Hervé.
Okay, thank you. I don't need to introduce myself. So, a question, Paul, about the effects of these big events on the valley setting, evidently, but also about the present fluvial pattern. So we go back to the question of catastrophism versus uniformitarism. So what is can we see some effects of these big events on the fluvial actual pattern? And it can be also a question for Michael. Another question for Michael is also, what about the connectivity? You have spoken about spatial complexity, but there is also, in this domain, the question of connectivity which link availability of sediment and capacity.
Well, the short answer is I don't know of any papers where anybody has looked specifically at the impact of catastrophic floods on later river evolution. But in a couple of papers I made some general comments that sometimes the scale of these features is so large that they cannot readily be effaced from the landscape. They're often additionally extremely porous because all the very fine material is exported down system, so there's no surface runoff. So they remain persistent in the landscape and they can constrain the course of subsequent channels. So you often have deeply incised rivers which are avoiding these sedimentary structures, which in principle are erodible, but in fact have not been eroded.
Okay, so just to follow on that, indeed, like I guess it depends on the context, but yeah, you produce a lot of sediment. If you are in a wide open valley, the moment the river starts incising, you may decouple the river system from the sediment supply, indeed, and that's observed like in Iceland, even in Scotland. I mean, there haven't been like extreme floods in Scotland, but there was work by Katie Whitbread that showed that the river starts incising into this U-shaped valley, but because Scotland is not very active technically, you just have a slot canyon, and you've got a lot of sediment on the benches that never really get into the channel. So there's exhaustion, the river don't have any sediment, but there's a lot of sediment there. So it's the question of connectivity, and maybe the connectivity thing here. What I gave in the talk was very general in the sense I was considering a reach scale, but the sediment supply to the reach is coming from the hillside, but there's also everything that comes from upstream. So in that case, the connectivity is very important. And that's one of the things that Ben Dan showed, for example, in their model. I don't know if that's going to work. You can see here that in that case, the further downstream you go, so the nature of the, you can see a lot of pulses. There's no sediment and then a lot, and no sediment and then a lot. But as you go downstream, the signals tend to amalgamate, and you've got much less of a pulse-like signal near the end. So obviously connectivity is very important, in particular when you go downstream the river system.
It was James Bathurst, yeah, over there.
James Bathurst, Newcastle University. I have a question for Paul. I like the way you ended your talk by saying that you could adapt your model as new examples of information came along. And an example of perhaps a rather more extreme environment would be another planet, namely Mars, where there are a lot of images that the images seem to suggest that there have been major floods of the same sort of catastrophic nature on Mars. And I wondered whether the images that we have from that provide enough information that they can be usefully used to constrain the sort of model that you're developing.
Well, people are increasing the... Oh, you should use them. It's a little bit surprising, but until quite recently, people who I call Martians were not using Earth analogs very much, but that's changed rapidly in the last 10 years. So Earth analogs are becoming very important for studying Mars, and I have to say, in my opinion, some of the behavior we see on Mars is becoming a very useful analog for things we can observe on Earth.
There's over there, Gordon.
Gordon Grant. I'm going to ask what I think is probably an obvious question to a lot of people sitting in the room, which have, after listening to two really, really excellent and very clear talks, I'm thinking about how to reconcile the stories that you're bringing us. On the one hand, Paul, you've given us a very clear sort of event-based, mechanistic look at how the stratigraphy and sedimentology of these big floods plays out and gives us some ability to interpret what's going on. Mikhail, on the other hand, has given us reason to doubt anything that we see in the record as being diagnostic of anything, as Mikhail, I think, already sort of pointed out. So how do we reconcile those? I mean, Paul, in other words, are you just giving us one example of a suite of potential stratigraphic records from big events as a function of some of the issues that Mikhail told us? And conversely, Mikhail, you know, you point to Benda and Dunn, and so that's suggesting that somehow, in spite of all the things and this is a model, but perhaps in spite of all the things that could possibly go either right or wrong in a basin, somehow some coherent sedimentological and bedload discharges do emerge. Otherwise, we really couldn't do our science. How do we reconcile all this?
Well, the short answer is I don't know, because, you know, the presentation I've given today is very much focused on extremely large floods, which have very clear, long-lasting effects on the landscape, which have persisted for thousands of years. And how those are now interacting with the modern system comes back to the question we had over here. I think, just picking up on a couple of points that Mikhail made, when you have large events in systems which are then subsequently inundated again, and that can't happen with the very big, gigantic powers, you often impose on the system some kind of landform, like a large cluster of boulders. But from observations we've made and some measurements, although these are introduced by a large flood, they appear to be static because they're there, flood after flood after flood. But actually, there's a flux of sediment through these features. A couple of boulders will go on one flood, and a couple more boulders will join that cluster. So they remain dynamic if you look at them closely, but if you look at them superficially, they appear to be static features. So they've been introduced by an exceptional flood, and then they persist, but in a dynamic sense rather than a static sense.
Right. So I'm sorry you perceive me as a messenger of doom or something like that, but it's not that bad. I still think that you know, big floods are capable of transporting large amount of sediment, so it's still very likely that you're going to transport, like the largest floods are going to export the largest amount of sediment. In that case, the examples that Paul talked about is the floods are so powerful, there's going to be export of sediment from the mountain to the basin, and that will be preserved in stratigraphy. The point that I've tried to make is that the biggest flood, like when you come into more moderate flood, I think the importance of the antecedent condition, I think is crucial here. And I'm not saying, oh, we can't do anything, we should just give up. We should see that maybe as a positive opportunity to try to understand better the coupling between the supply system and the river system. And I mean, I could almost answer by another question, is what gets preserved in stratigraphy? You know, are they the highest magnitude events? Are they the ones that follow a big supply event? I don't think. I mean, if anyone has an answer to that question, please come and talk to me afterwards. Thank you.
Maybe just the last question. There was at the back. Sorry. Was already.
Dave Milan, University of Hull. Question more to Michael, I think. You showed that some very large boulders had been transported. And I just wondered, there's some work that I've been doing on the South Tyne catchments following a big event in 2007. And one of the things that I noticed was movements of very large boulders up to almost a metre in diameter that appeared to have been deposited on top of the floodplain. So there was actually grass underneath these boulder deposits. And one of the things that came across my mind was the possibility of hyper-concentrated flows or non-Newtonian flows. So I just wondered what your thoughts were on the role of non-Newtonian flows in depositing those kinds of boulders.
Well, that's a very important point. I briefly mentioned that in the book chapter actually, but the example by Matter and Hartley in the Atacama, like it's suspected that it was actually a hyper-concentrated flow. So that's, I would say, another complication. I've seen that in a few places as well, like when you've got a river system, low gradient, and then you see these boulder bars, and you know there hasn't been like extreme floods in this area for a long time, and yeah, the possibility is that you've got something starting as a debris flow and coming down, and then the boulders can travel quite far. And I don't know if you've seen, most of you may have seen that video of a debris flow in Afghanistan. It's on YouTube, and it's a video that shows military people waiting, and they've been told that there's a debris flow coming. And you see the thing coming, and it's very impressive debris flow, like blocks the size of these tables, like coming down and tumbling and carrying on. But what I was really struck with is that when the camera moves and the blocks arrive and they reach a main river. So that was a dry channel. Debris flow comes down a dry channel, and then there's a river, like what looks like a mountain river. And the moment the debris flow hit the mountain river, nothing happens. The boulders carry on down, like there's no accumulation of boulder here. So it looks like something that started as a debris flow may behave more like has carried down that main river. And you may go downstream a few kilometers and you may find all these boulders, and the signature may look like fluvial, but actually it started as a debris flow. So I think these processes are probably very important in moving boulders.
Can I just add to that? Clearly big boulders can move by debris flows, but I wouldn't want to jump to that conclusion too rapidly. I've done a lot of work on initial motion of boulders, mainly in bedrock channels, and there's a couple of signal observations, is that after events, the boulders you observe are almost universally much larger than you would predict with normal competence equations. And one reason is that the drag coefficients are very, very large for irregular boulders in shallow flows, and the friction coefficient with the bed is very low. And although John Allen's concept of overpassing was related to rolling particles, you can go back and look at the overpassing theory to partly explain why you can get such large cubic boulders, if you like, irregular boulders, moving over relatively smooth surfaces.
Okay, I think it's time to close. So thanks again to the speakers. Fantastic presentations. So now it's coffee break time, I assume. Yep. So thanks.